So students, our next topic is called trigonometric functions of sum and difference of angles. Here we will learn some new trigonometric identities and we will try to prove them. So let's begin our discussion on this. The first identity we have here is that sine of minus x equals to minus sine x, which we have already learned previously. The second identity is that cos of minus x is equals to cos of x, which we have also seen before. Our next identity, identity number 3, it states that cos of x plus y is equals to cos x into cos y minus sin x into sin y. Now we will prove this. To prove this, we will take the help of the figure which is shown here. In this figure, we have our coordinate axis x and y, and we have our unit circle whose origin is at 0. In this unit circle, we have 4 points P1, P2, P3 and P4. We see that here the length of the arc P1, P4 is x, the length of the arc P1, P2 is y, and the length of the arc P3, P4 is minus y. And we see the corresponding angles subtended by this arc at the center of the circle. Now we know that the point P can be represented as cos x and sin x, since for P1 the angle is x, therefore the point P1, its coordinates will be cos x, sin x. For the point P2, the angle subtended is x plus y, therefore P2 will be cos x plus y, sin x plus y. For P3, it will be cos of minus y and sin of minus y. And point P4 is simply 1, 0. Now that we have this unit circle and the different points on it, we will now try to prove our identity. We see that the triangles P1O P3 and P2O P4 are congruent. Since these two triangles are congruent, we can write that their sides P1 P3 is equals to P2 P4. Now we have the line segments P1 P3 and P2 P4. To find the distance between P1 and P3, we will use our Euclidean distance formula, and similarly for P2 P4 as well. Using the Euclidean distance formula, we can write P1 P3 square is equals to cos of x minus cos of minus y whole square plus sin x plus sin y whole square. Thus, if we simplify this, we will get cos square x plus cos square y minus twice cos x cos y plus sin square x plus sin square y plus twice sin x sin y. Now we know that cos square x plus sin square x equals to 1. Thus, those two terms we will take and we will get 2. Now the equation becomes P1 P3 square equals to 2 minus 2 times of cos x cos y minus sin x sin y. We will take this as equation number 1. Similarly, we use Euclidean distance to find P2 and P4. So we write P2 P4 square is equals to 1 minus cos of x plus y whole square plus 0 minus sin of x plus y whole square. If we simplify this, we will find that P2 P4 square is equals to 2 minus 2 times cos of x plus y. We label this as equation 2. Now, since P1 P3 is equals to P2 P4, thus P1 P3 square is equals to P2 P4 square. Thus, we will equate equations 1 and 2 and we will see that 2 minus 2 times of cos x cos y minus sin x sin y is equals to 2 minus 2 times of cos of x plus y. So we can cancel the value 2 on both sides of the equation, and then we are left with cos of x plus y equals to cos x into cos y minus sin x into sin y. Thus, we have proved our identity. The fourth identity that we will learn is cos of x minus y is equals to cos x cos y plus sin x into sin y. Let's prove this. To prove this, we will use our identity 3 that we just learned, where cos of x plus y is equals to cos x cos y minus sin x sin y. In that identity, we will replace y by minus y. And let's see what happens. So, if we replace that, we get cos of x plus minus y equals to cos of x into cos of minus y minus sin x into sin of minus y. Now, we know that cos of minus y is equals to cos of y and sin of minus y equals to minus sin of y. If we put those values in our equation, we get cos of x minus y equals to cos x into cos y plus sin x into sin y. So, we have proved our identity number 4. Our next identity, identity number 5, is cos of pi by 2 minus x is equals to sin of x. To prove this, we will use our identity 4 and replace x by pi by 2 and y by x. Thus, our identity 4 becomes cos of pi by 2 minus x is equals to cos pi by 2 into cos x plus sin pi by 2 into sin of x. Now, cos pi by 2 we know is 0. So, the first term here becomes 0. Now, sin pi by 2 is 1. So, we replace sin pi by 2 with 1. Then, the second term becomes 1 into sin of x, which is just sin x. Thus, our identity cos of pi by 2 minus x is equals to sin x. The next identity, it says sin of pi by 2 minus x is equals to cos of x. Now, sin of pi by 2 minus x can be written as cos of pi by 2 minus of pi by 2 minus x. To prove this, we will use our identity 5. Identity 5 said that cos pi by 2 minus x is equals to sin of x. So, sin of pi by 2 minus x will be cos of pi by 2 minus of pi by 2 minus x, which is equal to cos of x. Thus, sin of pi by 2 minus x is equals to cos x. Identity number 7 says sin of x plus y equals to sin x cos y plus cos x sin y. Now, let us try to prove that. We know from our identity 5 that sin of x plus y can be written as cos of pi by 2 minus of x plus y. Now, this equation becomes sin of x plus y equals to cos of pi by 2 minus x minus of y, which is equals to cos of pi by 2 minus x into cos y plus sin of pi by 2 minus x into sin y. Here we have used our identity number 2. Now we also know that cos of pi by 2 minus x is sin x and sin of pi by 2 minus x is cos x. If we replace those terms, it becomes sin x into cos y plus cos x into sin y. Therefore, sin of x plus y is equals to sin x into cos x plus cos x into sin y. For our next identity, identity number 8, we have difference of the two angles. It says sin of x minus y is equals to sin x cos x minus cos x into sin y. Let's prove that. The proof for this is very simple. We will use our identity 7 and replace y by minus y. Thus, sin of x plus minus of y is equals to sin x cos of minus y plus cos x into sin of minus y. Replacing the values of cos of minus y and sin of minus y, we get sin x into cos y minus cos x into sin y. Now, if we take our identities 3, 4, 7 and 8 and replace them by suitable values of x and y, we can come up with these identities, which are cos of pi by 2 plus x is equals to minus sin of x and sin of pi by 2 plus x equals to cos of x. Similarly, cos of pi minus x is equals to minus cos x and sin of pi minus x is equals to sin x. In this way, we can get our other identities as well. In identity number 10, it says if none of the angles x, y and x plus y is an odd multiple of pi by 2, then tan of x plus y equals to tan x plus 10y divided by 1 minus 10x into 10y. Let's prove this. Since the problem says that x, y and x plus y are not odd multiples of pi by 2, hence we know cos x, cos y and cos of x plus y will not be equal to 0. Now we can write tan of x plus y as sin of x plus y divided by cos of x plus y. And again, we know because of our previous identities, sin of x plus y can be written as sin x cos y plus cos x into sin y. And cos of x plus y, the denominator, can be written as cos x cos y minus sin x sin y. Now, if we divide both the numerator and the denominator by the term cos x cos y, we will get this equation. And if we simplify it, we will get tan x plus tan y divided by 1 minus tan x into tan y. Thus, we have proved our identity. Identity number 11 says tan of x minus y equals to tan x minus tan y divided by 1 plus tan x into tan y. Let us prove this. To prove this, we will replace y by minus y in our identity number 10. Thus, identity number 11 becomes tan of x plus minus y equals to tan x plus tan of minus y divided by 1 minus tan x into tan of minus y. If we solve this, we get tan x minus tan y divided by 1 plus tan x into tan y. Identity number 12 says that if none of the angles x, y and x plus y is a multiple of pi, then cot of x plus y is equals to cot x into cot y minus 1 divided by cot x plus cot y. Since it is given that x, y and x plus y are not multiples of pi, hence sin x, sin y and sin of x plus y are non-zero. Now, cot of x plus y can be written as cos of x plus y divided by sin of x plus y. Then we simply replace cos x plus y by the identity cos x cos y minus sin x sin y, and we do the same thing for sin of x plus y. Then we divide both the numerator and the denominator by the term sin x sin y. When we simplify that, we will get cot x into cot y minus 1 divided by cot y plus cot of x. Identity number 13, it says cot of x minus y equals to cot x into cot y plus 1 divided by cot y minus cot x. To prove this, we will simply replace y by minus y in our identity number 12 and we can have our result. Let's move on to our next identity, identity number 14. In this identity, it says that cos of twice of x equals to cos square x minus sin square x, which is also equal to twice cos square x minus 1, which is equal to 1 minus twice sin square x, and that is also equals to 1 minus tan square x divided by 1 plus tan square x. Let us prove all of this. So, for the first part, we will take our identity number 1, which we have already learned, that cos of x plus y equals to cos x into cos y minus sin x into sin y. In this, we will replace y by x. Therefore, we will get cos of x plus x, that is cos of twice x. And on the right hand side, we will get cos square x minus sin square x. Thus, cos of twice x is equal to cos square x minus sin square x. Now, since cos of twice x is equals to cos square x minus sin square x, then sin square x we can write as 1 minus cos square x, because sin square x plus cos square x equals to 1. And if we do that, we will get cos of twice x is equals to twice cos square x minus 1 as shown on the screen. Now, cos of twice x is equals to cos square x minus sin square x. In this, we replace cos square x by 1 minus sin square x and we get cos of twice x is equals to 1 minus twice sin squared x.